Hello, and welcome back to California Geology. I'm Dr. Robert Lopez. Today I want to finish off the Sierra Nevada by talking about glaciers, and then later on we'll look at Sierra Nevada gold deposits. In order to study the glacial history of the Sierra Nevada, first we need to look at what glaciers are, how they work, how they erode, how they change the landscape. So looking at that first, glaciers really a slow-moving, thick masses of ice that move under their own weight. In fact, I always say the definitive characteristic of a glacier is the ability for it to flow, ability to flow. And in order to do that, it needs to be about 150 feet thick, 40 meters thick. In the Sierra Nevada, we mostly have a type of glacier called an Alpine Glacier down here. And Alpine glaciers are restricted to mountain valleys, and they're going to be much smaller than the continental glaciers, which really cover very large regions. Alpine glaciers are found in many parts of the world, in Alaska, Scandinavia, in Europe, in the Alps. One of the best examples is the Kaumba Icefall on Mount Everest. It's a big glacier that hikers who go up to summit Mount Everest have to walk on the glacier. And they usually, when they're walking on the glacier, they're going over crevasses, and the crevasses can be several hundred feet deep, and they're crossing these things on these metal ladders, wearing those steel crampons on their boots. Very sketchy, but nonetheless, they do cross the Kaumba Icefall. And so the Sierra Nevada is primarily affected by alpine, or another word we use these are valley glaciers. So we'll talk mostly about those, but let's just say a couple of words about the continental glaciers. For continental glaciers, they have to be at least 50,000 cubic kilometers or square kilometers in area, and they're unconfined by topography. In other words, they get so thick, 9,000, 10,000 feet thick, that they're bigger than mountains, so they can actually flow over mountain ranges. They just kind of flow out from the center out towards the edges of the continents. Today there's really only two continental glaciers, the one over Greenland, which is melting quite rapidly, but that's maybe around 9,000 feet thick, and the one in Antarctica is close to 12,000 feet thick, so quite large. Now, glaciers today hold about 28 to 29 million cubic kilometers of frozen water. So if these glaciers were to melt, sea level would rise by about 70 meters, 230 feet. A couple other things about the Pleistocene. The Pleistocene is known as the Great Ice Ages, and we'll say more about that in a little bit. But during this time, there were continental glaciers over Canada, Northern Europe, and Russia. In the western U.S., we had glaciers going down as far south as maybe British Columbia, the U.S.-Canada border. But in the Midwest, the glaciers went all the way down to Kansas and in southern Illinois. We see glacial features. New York City, in fact, Long Island itself is really a moraine left behind by the glacier. Some glacial geologists will explain that the glacier thickness in New York City was about as tall as the Empire State Building. And so all that water on continents, much more voluminous glaciers, meant sea levels were lower, 130 to about 140 meters lower. All right, let's look at these alpine glaciers. We're going to focus on the Alpine Glacier. Now for the Alpine Glacier, remember we're looking at a valley. They're smaller than continental glaciers, restricted to mountain valley, but they can get quite thick. They can be 2,000 to 3,000 feet thick in these deep valleys that they form. Now, a couple of features that I've already drawn here. Here we have the Sierra bedrock, and then this would be the ice that I'm drawing here. And so the first one we want to really talk about is, or at least an important part of a glacier, is its budget of ice. And it's going to accumulate ice in one region and lose ice in the other. But the key thing about the glacier, that internally it's always moving. The glacier could be sitting there looking stagnant for years, centuries, but in reality, inside the ice is moving. It's always moving, at a rate of anywhere from 15 to 60 centimeters a day, which is about almost a foot a day. So it's moving continuously, always moving. And with that, there's going to be frozen rocks and sand and silt in here, all of these frozen rock. And so when the glacier is moving, even though it may be looking like it's standing still, this rock is moving down slope, moving, and eventually gets spit out over here at the terminus. In fact, this part of the glacier is called the terminus. So at the terminus, it gets spit out and it's going to leave a deposit. And so this deposit here is called moraine. So moraine is a glacial depositional landform. We'll talk more about moraine here in a moment. So this frozen rock, right, really leads to a glacial erosion feature called abrasion. So this is really due to the frozen rock and sediment in the glacier. So this frozen material is the stuff that's sculpting, polishing, scratching the bedrock. And really the ice by itself kind of deforms and flows, so it really is quite weak against the rock. But what's really doing the abrasion is the frozen rock within the ice that's being continuously moved down the valley. Some of it's being plucked from underneath. Some may fall from adjacent valleys, from adjacent highlands or peaks. You might get some rock falling onto the ice and then sinking down to the bottom over time, being scraped off there. So glacial erosion is really happening by two ways. One is this abrasion, which is the frozen rock and sediment, polishing, sculpting, scratching the ice or the bedrock. The other way is plucking. And plucking is a little unusual in that you need water. But you have frozen ice down here, so it's really hard to get the water. But water is kind of unusual. The way the water is going to get is as ice is moving. Let's say there's a little bump in the bedrock here, and what's going to happen is you're going to build up quite a bit of pressure behind that little bump. As you build more pressure, water is very unusual. So here's a little graph showing increasing temperature. So if you increase the temperature, you make vapor, steam. If you have a little bit more pressure, you'll have liquid. But over here, if you have ice at a colder temperature, maybe you'll keep that same temperature, but if you increase the pressure, you cross this line between ice and liquid, so you convert the ice into a liquid. So this pressure melting occurs in liquid. So as you apply higher pressure to the ice, you can actually cause it to melt. And it's really due to the structural nature of the water molecule. So anyhow, so what we see here, we see this pressure building up here. Then we'll get the liquid water down here, H2O forming down here, and that can allow the plucking to occur. So you'll pluck large pieces of the bedrock or a variety of pieces of bedrock, and they end up moving down with the glacier ice, right? So again, the glacier ice could be sitting here for centuries, not appearing not to move, but internally it is flowing like a conveyor belt. Now, other features about this budget that I was talking about. So note that there will be a zone in here that we call the ELA. And the ELA stands for the equilibrium line of accumulation. So I have it written down here. Equilibrium line of accumulation. And it's the lower limit of snow accumulation, right? So during a colder climate, this ELA would be farther down the valley because you're going to have a larger zone of accumulation. During warmer climates like today, the ELA is pretty much over here at the head wall of the glacier, where the glacier begins. So with that ELA, it's going to separate a zone up here called the zone of accumulation, and then the zone below is going to be the zone of ablation. And ablation in this case means melting, where the ice is melting faster than it's accumulating. Sometimes this zone of ablation is also termed the zone of wastage, right? Where the zone of wastage versus the zone of accumulation. Now, other features we should point out is where the glacier begins, just like rivers. Rivers begin in the headwaters. Glaciers begin in a place over here called the head wall. So up here we'll have the head wall. And the head wall will always be the bedrock, Sierra bedrock here. And then there will always be a separation here, a separation between the head wall and the ice. And as the ice is moving, being pulled downhill, it's going to separate from the head wall and make this crack here called the bergschrund. So this bergschrund, so down here I have the bergschrund spelled out here. It's a break between the glacier and the rock face head wall. So the bergschrund will be up at the top there. And then note that we have these cracks in the ice here. So these cracks are known as crevasses. And the crevasse is a crack in the ice. They can be several hundred to 1,000 feet deep, depending on how thick the ice is. And they're forming in an area of the ice where the ice is behaving brittly. So it's brittle up in this region here. That's why these cracks form. But scientists have found that as you go deeper in the ice flows and deforms like plastic. So down here we call this a plastic deformation or ductile. So this would be ductile down here. So there is a transition between a ductile deformation deeper down and this brittle deformation up near the top. So that would be where the crevasses occur. All right, and so that's the little dash line I drew here refers to that brittle to ductile transition. Now, let's see what else we have here. So we talked about the terminus. And so as the debris that's being moved down by the ice eventually forms these moraines. And so you can see I've drawn two other ones here. So usually the one at the end is obviously called the end moraine, because that's the one that occurs at the end of the glacier. But over here we see others that indicate the glacier was farther down the valley in the past. In fact, this one over here that marks the farthest extent of the glacier, we usually call that the terminal moraine. And this terminal moraine marks the maximum extent of the glaciation, how far it got down the valley. Or in the mid-continental region, like in southern Illinois, we find terminal moraine for the last glaciations that affected the North American continent. But then as the climate warmed, the glacier started to melt back. And we see maybe the glacier stalled for a while here, 50, 100, 200 years. It stalled there as it was melting back, and it left another moraine. And so we call this one a recessional. So recessional moraines occur. They're embedded within the terminal moraines as the moraine is melting back. Over time, if this glacier starts melting back more, this end moraine will become another recessional, and we'll have another end moraine at the terminus of the current glacier. So those are some of the important features. Note that this drawing is similar to the one on page 200 of your book. Now, earlier I mentioned that the typical rates of an alpine glacier advance is anywhere from 15 to 60 centimeters per day, 6 inches to 24 inches. Sometimes there's a surge where you can get maybe 100 feet per day. That's during warmer summer climates where maybe enough water may get under the glacier to have the glacier sort of slip. So as glaciers move, it erodes the valley floor and the sides and carries the rock debris down with it. In fact, that's another term we need to point out. We talked about moraine. So the key thing about the moraine, it's a glacial landform that's left behind. It's a depositional landform. It's a ridge. But it's composed of all these boulders and gravel size and sand and silt, a variety of very poorly sorted sediment. So that's called till. So till is a general word we use for anything plucked, carried, and dropped off by the glacier. So we'll say material, plucked, carried, dropped off by the glacier. So there it is. In fact, let's stop here and then we'll continue on in a little bit here.